Hello everyone. In this video we will talk about the inverse Laplace transform method. This is a continuation of our previous topic, Laplace transform. This is the definition for the inverse Laplace transform. We have already used this script L when we apply on a function f of t that gave us the Laplace transform represented by this capital F and the independent variable s. Now we just define the inverse operation and we call this as the inverse Laplace transform method, which is given basically the inverse of this Laplace transform applied on f of s. It will give us the original f of t that we started. Let's look at some examples and that will help us to understand more clearly. So previously we have already calculated the Laplace transform of various functions such as a constant, and we have obtained the Laplace transform of 1 is given as 1 over s. Therefore, if we do the inverse operation here, we can say the inverse Laplace transform of 1 over s equals to actually 1. You can extend this to some similar expressions. What about the inverse Laplace transform of 3 over s, for example? Well, this 3 is a constant and we can take it out of the inverse Laplace transform. This can also be done in a Laplace transform or inverse Laplace transform method. We can take out these constants out of the expression. And then we are left with this 1 over s. But we know that the inverse Laplace transform of 1 over s is just 1. Therefore, we obtained the result as 3. Here's another example. We have studied before the Laplace transform of an exponential. And for this e to the power 2t, that was given as 1 over s minus 2. Therefore, if you apply the inverse Laplace transform on both sides of the equation, basically we get that the inverse Laplace transform of 1 over s minus 2 is given by exponential 2t. Similarly, if we have a constant 4 over s minus 2, you can take out the constant and then focus on this expression. And we know that this is the e to the power 2t. And just write down the result here. What about the Laplace transform of minus 1 over s plus 3? Well, we can take out the minus sign as we have here, and then focus on what's the inverse Laplace transform of 1 over s plus 3. But again, make the analogy with the previous example, and we can say that this is actually the result of this inverse Laplace transform is e to the power minus 3t. And that gives us the final result. Another example, what's the inverse Laplace transform of 1 over s cubed? This expression. Well, remember, we have the Laplace transformation rules, and if we have a polynomial such as the Laplace transform of t squared, we know that this will be equal to 2 factorial divided by s cubed. But we can always adjust this constant term easily by multiplying and dividing by this 2. We didn't change anything, but we make it look like this expression here. That's what we want. Because now I can take out this 1/2, and then I have 2 over s cubed, just like as in this expression, where we know the Laplace transform of t squared equals to this expression. Therefore, we just go and do the reverse operation and write down that this is 1/2 times t squared. Okay. Here's another similar example where we want to find the inverse Laplace transform of 2 over s squared. And from our previous knowledge, we know this. that the Laplace transform of t equals to 1 over s squared. Therefore, the inverse Laplace transform of 1 over s squared is actually equal to t. But we can take out this coefficient, so that gives us 2 times t. In this example, we are given the Laplace transform of the sine function is actually equal to, for sine 3 times t, that is equal to 3 over s squared plus 9, where we consider 9 as k squared actually. So we have k equals to 3 in this example. And this one is asking what's the inverse Laplace transform of 2 over s squared plus 9. As we said, you can easily adjust the constant here. So basically we are looking for the inverse Laplace transform for this expression. But this is not difficult, so we can make it look like this one. So I want to have 3 over s squared plus 9. And in order to do that, we can take this, we can rewrite this basically 3, and then we have 1 over 3 times 2, because we have 2 over s squared plus 9. So we didn't change anything, we just multiply and divide by this 3, and then we take this 1 over 3 times 2 out of this expression, and I'm left with 3 over s squared plus 9. And now we again have a similar expression where we might remember from our previous Laplace transform examples. And in those examples, we have already seen this type of expression actually is the Laplace transform of sine 3 times t. Therefore, you can just substitute this as sine 3t, and that gives us the result 2 over 3 times the sine 3t. Another example, remember for the cosine function, we know from, again, Laplace transform methodology that the cosine at equals to s over s squared plus a squared. Now the question is, what about the inverse Laplace transform for this expression, s over s squared plus 3? Now, these two, they look quite similar to each other, right? The only thing you need to do is write down what's the a in this equation here. And that's not difficult to guess. Basically, you have s squared plus a squared. So a squared corresponds to 3. So that means a equals to the square root of 3. And then you can directly now substitute back in this cosine formula. Since this is our a, then basically the result will be cosine of square root of 3 times t. Here's another example. Now, what's the inverse Laplace transform for this expression? Well, in order to take the inverse Laplace transform, we need to split this into pieces and consider first take care of this s and then take care of this 1. So this is our first piece, and then we have the second piece here. And again, for convenience, I multiply and divide both numerator and denominator with the 2 over 2. It doesn't change anything in my original equation. I just divide and multiply with the same number. And I remember, or I should note that for the cosine hyperbolic cosine hkt function, the Laplace transform actually corresponds to s over s squared minus k squared. And this k, as we see here, equals to 2. And for the sine hyperbolic function, we have k over s squared minus k squared. So now, in the light of this information, we should think about what we have in our problem and then try to write down the inverse Laplace transform for these expressions. And it is you can make the analogy easily. So you see, for example, here we have s over s squared minus 2 squared, and again it looks like this one, right? So that corresponds to actually cosine hyperbolic 2 times t. And then for this expression here, what do we have? Actually, this corresponds, if you think about this 2, so you can take this one of the 2 here, you can take it inside. And since this is k equals to 2 and we have 2 in the numerator, basically that means we can write this as the hyperbolic sine function 2 times t. And then we have this 1/2 here. So that gives us sine hyperbolic 2t over 2. Now, in this example, we are asked to find what's the inverse Laplace transform of this fractional expression. Now, in this type of expressions, your goal is try to simplify this as the sum of these as the sum of two expressions that are more simple. For example, if this is my ratio, now I can reconstruct or decompose this in terms of two simple fractions like a over s minus 2 plus b over s plus 1. And then basically it's an equation to solve for us. We need to multiply this side by s plus 1 and multiply the other side by s minus 2 and then solve for the unknown coefficients a and b. I mean, this is a somewhat simple linear algebra for you. You have the left-hand side in the numerator, s plus 3, and in the numerator on the right-hand side, we have a times s, and then we have plus a, because we are multiplying with this guy, and then we have b times s minus 2 times b from these equations. And then just solve these, and you will find that a equals to 5 over 3 and b must be equal to minus 2 over 3. So once I found the a and b, that means I'm almost done in terms of decomposing this expression into something more simple. And this is what we do here. We decompose this expression into these inverse Laplace transforms for these basic functions here. And remember, we already know that the inverse Laplace transform of 1 over s minus 2 is equal to the exponential 2t. And here we have the exponential minus t. Just combine these two and you will get the final result that is given in terms of the exponential 2t and exponential minus t. Now, in this example, we are given a fractional expression in terms of s. Remember, for these type of expressions, always it is easier to work with more basic fractional expressions. So we can see that the denominator is s plus 2 times s minus 1. So that means in this expression, I need to decompose this in terms of these individual expressions where we have a over s plus 2 plus b over s minus 1. So my goal again is to solve for the unknown coefficients a and b. And that's not very complicated. You just simply write down the left side in the numerator and then right hand side. And then we match, we obtain these two equations from this problem. And then I can simply sum these together, and then 3 times b equals to 9, b equals to 3, a equals to minus 2. And finally, now you can substitute these back to our simplified representation. Just plug in these back. And that gives us minus 2 times, we have minus 2 here from A, inverse lambda of 1 over s plus 2, plus we have here 3, times the inverse Laplace transform 1 over s minus 1. And we know that this is given in terms of exponential t, and this is given in terms of exponential minus 2t. So now just combining the result, we can write down the final solution for this problem. Here's another example where we have two expressions in terms of s and s squared. Well, remember, just like the Laplace transform, inverse Laplace transform method is also linear. So we can separate and apply the inverse Laplace transform to individual expressions. And you can see for the inverse Laplace transform of 1 over s plus 5, that is exponential minus 5t. And similarly for the other guy, we can write this as the inverse Laplace transform of 1 over s squared plus square root of 3 squared. As you see, we just rewrite it. We have written this again, and then we multiply and divide by the square root of 3. And doing this, we can take one of this square root of 3 inside into the numerator, and then this gives us the sine square root of 3 times t as the inverse Laplace transform for this expression here. And then we have a division by this square root of 3. So we just repeat that, write it down, and we have the coefficient 7 here. For the other side, for the other guy here, I think this is even simpler for you, because the inverse Laplace transform of 1 over s plus 5, that is given by the exponential minus 5 times t. Here's another example. We are given the result of the Laplace transform. The question is asking us find the inverse Laplace transform for this given function f. Well, what can we do? Remember, we can, if we are given in this type of format where we have two or multiple expressions multiplying each other like this one, then we can decompose this as a over s, and then b over s squared, and then c over s plus 2. Now we need to equate the denominators. This guy we need to multiply with s times s plus 2. This guy we need to multiply with s plus 2 and s squared. So just do the matching with the left-hand side. The left-hand side is s squared plus 1. And then on the right-hand side, we have this expression. But you can open this and modify a little bit to simplify. And that gives us basically these three equations as a result. Because once I try to solve the left side and right hand side equate to each other, I obtain these three equations, and we can solve them to obtain these a, b, and c values. And finally, we need to combine now all these results all together. An inverse Laplace transform of this expression now is given by this minus 1 over 4, because we calculated this a, so that is minus 1 over 4, as you see, and then the inverse Laplace transform of 1 over s. But we know that this is just 1, so we have this constant minus 1 over 4 times 1. And then what about the inverse Laplace transform of 1 over s squared? But from the Laplace tables, we know this is equal to t. So we can write down 1 over 2 times t. And also calculate this guy and then write it down here. And as you see, this is something we have already done. The inverse Laplace transform of 1 over s plus 2, that is given by the exponential minus 2 times t. So we just write down everything, each piece, and that gives us the result. Now let's look at to this example. This is the inverse Laplace transform. We need to apply it to each of these terms. As you see, we have 4 different terms here, and I need to apply the inverse Laplace transform for each one of them. For example, for the first guy, we know that this is just 1, and then for the second term, the inverse Laplace transform of 1 over s squared. But we know that this is equal to t. And similarly, the inverse Laplace transform of 1 over s cubed, we know that this will be given as t squared over 2. And then similarly, for the 1 over s to the power 4, we have t cubed over 6. And now once we calculate it for each term, then just combining them, we can see the result should be equal to this expression. Here we have another example. The inverse Laplace transform for these 3 expressions. And in order to calculate this, again, the critical thing is to represent everything in terms of something we have already known from the Laplace transform results. For example, 1 over s minus 2, this is clear. We already know that this corresponds to the exponential. So from here we can really easily and directly write down the inverse Laplace transform, because this is something we are already familiar with. And then the inverse Laplace transform of 1 over 2 times s plus 1 half. And again, except this 2 here, we know how to take care of 1 over s plus 1 half, right? We know that this can be written again in terms of the exponential function. But we just need to make sure this 1 half, we take it out, as you see, because otherwise we cannot obtain this exponential. So once we take out this constant term, here this expression is now familiar territory for us, because we can say that this corresponds, the inverse Laplace transform of this expression corresponds to e to the power minus t over 2. And remember, we have the coefficient here. And finally, for the third expression, again, notice 1 over s minus 3. This is again related with the exponential function when we take the inverse Laplace transform. So we can directly say that this is equal to the 1 over 3 times e to the power 3 times t. So when we combine all that together, that's our solution for this problem. Now another example, we have 3 expressions here, and for each one of them we need to apply the inverse Laplace transform method. So we need to apply this 3 times. But most of these expressions, I think you have already now got familiar and can guess what should be the inverse Laplace transform correspondingly. For example, you will start, we have the inverse Laplace transform. So basically this 3, for example, which is a constant, you can take it out. You can take it out. And then we have the inverse Laplace transform of s over s squared minus 2 squared. But we will remember from our last lecture that the hyperbolic cosine kt, the Laplace transform, that is given as the s over s squared minus k squared. And similarly for the sine hyperbolic k times t, we actually remember from our previous lecture that this Laplace transform equals to k over s squared minus k squared. Now by looking to these, we can easily make the analogy in the above problems, like s squared minus 4, and we have s in the numerator. So that means basically the first one looks like our cosine hyperbolic k times t, right? And this 3 is out. So this expression gives us the hyperbolic cosine 2 times t, because here we have k equals to 2. basically we are able to handle the first one. For the second expression, look at this. We have s squared minus 1, where 1 you can consider as 1 square, which is also 1. So basically, it reminds us this guy, where we have this k equals to 1, right? If k equals to 1, this is 1 over s squared minus k squared. That corresponds to our sine hyperbolic function. We still have this minus 2 outside here, and then we multiply with the sine hyperbolic of t, because k corresponds to 1, right, in this example for the second one. If we look at the third one now, we have s divided by s squared minus 1/2 squared. And for this one, remember this again, s over s squared minus k squared. This resembles to the cosine hyperbolic function. So we can say in our example here, k, this corresponds to k equals to 1/2. And then we can immediately write down cosine hyperbolic t over 2, as you see here. Now, in this example, which is actually similar with the previous example, we have two expressions in terms of s, and we want to do the inverse operation and calculate the inverse Laplace transform. Well, first start by splitting this into two expressions. Take out the constants, okay? You can take out them and then rewrite this as inverse Laplace transform of this one and the inverse Laplace transform of this expression. But we have already mentioned in the previous slide that this expression here corresponds to the hyperbolic cosine function 3 times t. So this is the hyperbolic cosine function, and here our k, this k corresponds to 3. And in this guy here, k corresponds to 5. So basically we have 4 times the cosine hyperbolic 3 times t, and then we have 3 over 5, because we want to take, in the numerator here we have 5 missing. In order to complete that, we take this 5 inside, and then we are left with 3 over 5 times the sine hyperbolic 5t. So these are all the examples for demonstrating the application of the inverse Laplace transform method. Thank you for watching.